for the semester. Okay, so we've been talking here about sort of the effect of really sort of temperature on the rate of a reaction. We talked about sort of the activation energy, and again, that minimum amount of energy is required really for a reaction to take place. What that really means, it's really that sort of barrier, that energy barrier or hill, it's sometimes referred to, that as the reactants are really starting to basically react and starting to break their bonds and starting to make their bonds, is sort of the energy that they have to climb really to get to the other side. We've talked about that there's only sort of a certain proportion of molecules that do possess the right amount of energy to do that and also get to the other side. And again, a couple of things we touched upon, obviously increasing the temperature increases the energy, allows the reaction basically to occur faster, just simply because everybody has more energy. There's a greater proportion of guys that can get up and over to the other side. And we see that in sort of a faster formation of products, for example. Opposite is true, like we've been talking about, that obviously lower, we see a lower proportion of sort of guys that can get up there. Again, energy is really an important factor. Also, again, that sort of collision theory is sometimes referred to as everybody sort of colliding in sort of the right orientation. So just because, again, two things sort of collide with each other doesn't necessarily mean that you'll always get sort of products being formed. So that sort of right amount of energy, the right sort of active side, if you will, in terms of the collision is sort of really important in terms of that. We saw a couple of sort of equations that really do relate sort of temperature to the rate constant and the rate of a reaction. One, again, is more of a graphical sort of approach that we oftentimes will use, where you have maybe a bunch of data points of rate constants, maybe some temperature values and stuff like that. And then you can do a graphical sort of approach to figure out something like activation energy. We did a couple examples just a second ago about using sort of a 2-point version of that equation, the Uranus equation, to basically determine the activation energy. So I'll try one more here before we finish up talking about sort of mechanisms and stuff. Let's take a look at an example here. We just make one up maybe here. There we go. All right, let's say we had a reaction. This reaction had a activation energy of 105 kilojoules and a rate constant of, let's go with 5.2 times 10 to the minus 10 reciprocal molar seconds at, let's do 27 degrees Celsius. What would be the rate constant at, we'll do 47 degrees Celsius. All right, take a couple minutes and sort of see what you come up with on that one. Okay, so let's take a look at this. So again, a couple of things. In this case, we do have the activation energy given to us at 105. We do have a rate constant given to us, which would be, we'll just label it number 1 since it was the first one there, 5.2 times 10 to the minus 10 molar seconds, reciprocal seconds. That goes with a temperature of 27 degrees Celsius. We are looking for another rate constant, so we'll call that one 2, and that goes with a temperature of 47 degrees Celsius. So again, this fits very nicely into the equation we've been using, which is natural log of K2 over K1 is equal to E of A over R, 1 over T1 minus 1 over T2. We do need to do a little bit of conversions here. We obviously need to convert our temperatures into Kelvin. So that's going to give us a, looks like maybe my calculator works there. There we go. 300 Kelvin here. a long way to go to get to 300 Kelvin. And if we had 273 here, I'm looking like a 320 Kelvin happening in this case. Now, we got pretty much everything else we need except for K2. So again, we could kind of plug our guys in. This would be the natural log of K2, which is what we're looking for. Our K1 being the 5.2 times 10 to the minus 10 seconds there. It's a big thing for units there. E of A is 105. I am, again here, like I did previous chapters, I'm going to multiply that by 1,000. Because it is in kilojoules, remember that R is in joules. So again, I'm just going to do that so that they are in the same units. Remember that you do need to do some type of conversion there to get them in the same units. Otherwise, you will be off by that factor. So again, you could go to kilojoules on both if you wanted to, but here I'm just going to go to joules. Our T1, which should be this guy, is 1 over 300 minus our T2, which is 1 over 320. All right, so we actually, in this case, can clean up everything there on the right-hand side. So 1 divided by 300 minus 1 divided by 320. We're then going to times it by 105 times 1,000. And then finally, we're going to divide it by 8.314. That's going to give us a natural log of K2 over 5.2 times 10 to the minus 10. I'll get rid of the units to make it a little bit neater. 2.631104.162. Don't feel like rounding. To get rid of the natural log on the left there, we do need to take the E again of both sides. Other very common mistake that people do is they want to put a negative there on the right, but there is no negative, so you shouldn't do the negative. That's going to give us just the same thing that we got going on there, K2, 5.2 times 10 to the minus 10. Again, just taking the E of that number, no negative or anything like that, will give us 13.889. To finally figure out our K2, we're going to multiply our K1 to the other side, and that will get us a K2 that is 5.2, whoops, 5.2 to the minus 10. And you get a bunch of zeros and a 7 at the end, or if you put your calculator in scientific notation, you'll get something like 7.2 times 10 to the minus 9. Again, are a bunch of zeros and 7 if you ran out of digits on your calculator. Unit-wise should be the same units as this rate constant, and that would be molarity, reciprocal seconds, and our molarity, reciprocal molarity over reciprocal seconds. Question on that calculation there. Now, do we see sort of what we would anticipate? Well, if we look at our temperature here, we went from basically 27 to 47, which means that our temperature is increasing, which means we would expect the rate of the reaction to also increase. And it did, right? Our second rate constant there is, twice as big almost as our first rate constant there. So the rate of this reaction would increase, obviously, as a result of that temperature increase. Any questions on activation energy? As you can see here, you obviously can solve for a variety of things, including rate constants, temperatures, and so forth. Any questions on that? Okay. So we've been talking about it a number of times, but here's just sort of a graphical illustration of what we were talking about in terms of sort of that collision idea or collision theory. Just because, two things sort of run into each other, they do need to, like we've been talking about, sort of run into each other in the proper orientation with a sufficient amount of energy. So up on top here, sort of the purple guy will then leapfrog over to the orange, if you will, freeing up our CH3 over here. Now, if these same two things collide versus this is the carbon side, basically. Carbon side, this is the iodine side on this side. And if these two guys sort of collide with the carbon side coming in, we actually will not get products formed. So again, just because we get collisions does not necessarily always translate into products being formed. Again, that idea, as we've been talking about a number of times today, the idea of you need to hit in sort of the right location, and then also you need to have the sufficient amount of energy for that reaction to take place. And again, just one of those two things does not necessarily guarantee that you will get products that are being formed. Any questions on that there? Okay, so one of the last major things we're going to talk about is what is referred to as reaction mechanisms. And reaction mechanisms, there's some different types of reaction mechanisms that we will see, but it's basically based on that idea that if you remember like Hess's law and some of the other things that we talked about this semester, when we think about a particular reaction, for example, A plus B goes to like, E plus F, right? We oftentimes sort of visualize that, hey, this reaction maybe is like a one-step program here. Like it just goes from like reactants to products. And that's not necessarily always the case, as we saw with perhaps Hess's law when you did those type of problems, maybe last semester. We saw it as well with, say, something like equilibrium, even some delta H's, delta S's, those type of things. Sometimes reactions take place in multiple steps, multiple individual steps that lead to sort of a product being formed. So perhaps this reaction doesn't really happen in a straightforward one-step sort of program here. Maybe the first thing that happens is, maybe we make some C and D, and maybe C and D come through and then make our E and F. And then obviously, if we add these together, these guys sort of cancel out. They were referred to maybe as intermediates, and we actually do get sort of the overall reaction. Maybe it's a one-step program, two-step program, three-step program, four-step program. So what reaction mechanisms sort of try to do is outline a sort of probable explanation for how a reaction could take place. And again, this may involve several sort of individual steps. So when we look at a reaction mechanism, oftentimes what we're looking at is a set of what are referred to as elementary steps or elementary reactions. So we look at this overall reaction as really a sum of these sort of individual steps that lead us to sort of the product that's being formed. Now, why do we think reactions perhaps don't happen exactly as they're written in sort of a lot of reactions in a one-step sort of process? For example, if we look at this reaction that we see here in the middle of the screen, we have some NO gas there plus some oxygen gas making some NO2 gas, which when this reaction actually takes place, another sort of gas there is sort of detected. N2O2 is actually detected during this reaction. If we look at the overall reaction, though, we see pretty much no N2O2 found anywhere in the overall reaction. So what does that basically imply? That implies that perhaps this reaction doesn't occur in a boom, boom to the products type of thing, one type move from reactants to products. There has to be somewhere along the way that the production of N2O2 occurs. And there also has to be somewhere along the way where that N2O2 then is gone and used up. So that would imply that this reaction perhaps doesn't occur in a one-step fashion, that there may be multiple steps that occur in this particular formation of the product. And that's where we get something down here, which is like a proposed sort of mechanism. And they're made up of these sort of two elementary steps, a way to sort of explain maybe what we're witnessing here in this particular reaction. In this sort of explanation, like the first step is these two NO guys come together and actually form N2O2. And that would definitely explain why it is seen are detected during this reaction taking place. Why is it not in sort of the overall reaction can be perhaps explained by the second step. What ends up happening in the second step in this mechanism is the N2O2 and some O2 react and actually form our product. And what we end up with, if we add up the overall reaction here, is the N2O2 will cancel out. Everything on the left-hand side stays on the left-hand side, 2 NOs and 1 O2. Everybody on the right-hand side stays on the right-hand side, and we have our 2 NO2 sort of made here in our overall reaction. This N2O2 was made here in this mechanism, and then it was used up here. And that is basically what is known as an intermediate in this reaction. An intermediate is basically a substance that is produced early on in sort of the mechanism of this reaction, but does get completely used up by the time the reaction is over, which means it does not appear in the overall reaction. And again, this accounts for why when they do this reaction, they do detect that N2O2 there, but again, not present when it's all said and done. So this is a nice way to sort of summarize sort of how this reaction takes place. And that's sort of what reaction mechanisms try to do. They try to explain how a particular reaction could take place. And as we'll talk about, does that mean it takes place like that every single time? And it may not, but it is sort of a plausible explanation as to how a reaction could perhaps take place and explain why a reaction or how a reaction will actually sort of occur. And that's what we sort of see here again, this sort of formation of this intermediate. It gets used up, again, explains why this is detected in the reaction, but not seen in the overall reaction because, again, it sort of gets gobbled up in the second step of the mechanism. And that's an important distinction for what makes something an intermediate. An intermediate is something that, again, gets made early on in a mechanism, but the key part of that is an intermediate cannot be found in the overall reaction. So it does need to get used up in a later step. So in order for something to sort of qualify as an intermediate, we need to make it, and then we need to completely use it up by the time the reaction is done. And that's what we see here again with our N2O2 in this particular reaction we were just looking at. We definitely make it there in that first step, and then we use it up in that second step. And again, these are simple elementary steps to explain how this overall reaction sort of takes place. Again, very similar to where you kind of use different reactions to build an overall reaction. When we talk about these sort of elementary steps, we also talk about sort of, what's reacting or how many molecules are reacting in each of the elementary steps. And that is what is sometimes referred to as the molecularity of a reaction. And there's three sort of classifications usually. There's unimolecular, which means that there's only one molecule reacting in an elementary step. There's bimolecular, which means there's two molecules sort of reacting in an elementary step. And there's termolecular, which means that there's three molecules basically reacting in an elementary step. And again, we can see there the N2O2 plus the O2 would be bimolecular. Again, two molecules basically reacting in this elementary step. Now, one very different thing that we do in terms of rate laws that is very different from everything else that we've been talking about in this chapter is when we are specifically dealing with mechanisms and elementary steps, we can use the coefficients in those elementary steps as the orders for our rate law. So this is the only place sort of in kinetics where it is acceptable in a elementary step to use the coefficients as the orders. So what that means is, again, for example, here coefficient would be 1a. We could write a rate law for this elementary step of the rate is equal to k times a, really to the first. Again, we don't typically put the 1 there. Obviously, both of these guys are coefficient of 1, which means if we write the rate law, again, only for reactants for this particular elementary step, which is a bimolecular, 2 guys reacting, this would be an order of 1 and an order of 1 for this guy as well. This is basically a plus a, which is a fancy way of saying 2a, I guess, right? And the 2 here is where that 2 comes from. So if you remember everywhere else that we talked about in terms of kinetics, when you do regular kinetics problems and so forth, you cannot use the coefficient as the orders. But here in elementary steps, we can do that again because, you know, there are these individual steps and they allow us to use that information to basically determine sort of is this mechanism correct or not. And it's basically one individual sort of reaction, kind of the stoichiometry involved there allows it to work out okay in this particular instance. So again, just to be clear, if you're doing a kinetics problem like we did at the beginning of this chapter and so forth, you do have to use the kinetics information given to you to determine the orders. If you're working strictly on a mechanism type problem and using these elementary steps, it is the only place where it is okay to use the coefficients as the orders. So how do we know if a mechanism is perhaps a good mechanism or a bad mechanism or a plausible mechanism, it is sometimes referred to? There's some different types of mechanism problems, which we'll go through here in just a bit, but one of the two major things that we're looking for in order to, if you're given like a proposed mechanism, which is sometimes a question like, hey, this is the reaction. And they oftentimes will tell you in this reaction, the experimentally found rate law was this. And they'll actually give you the sort of experimentally found rate law, usually in some mechanism problems, not all, but in some. And when they do that, there's really two major things that you need to make sure are correct in order for it to be sort of a plausible mechanism or a good mechanism. The first one is pretty simple. When you add up all the individual elementary steps that are outlined in a particular mechanism, it needs to add up to the overall reaction that you're dealing with. So for example, like we just looked at on the previous slide, previous page there, obviously when we added up these two reactions, we got the overall reaction. And that's really the first thing that you need to make sure in order for your mechanism to be perhaps a possible mechanism or a plausible mechanism. If you add up all the elementary steps and it does not equal your overall reaction, it's probably a bad mechanism. It's not a good mechanism. It's probably not going to happen that way. So that's kind of the first major hurdle that you want to look at in terms of whether or not this mechanism is sort of good or bad. The second one can be a little bit more difficult to determine, and we'll talk about a couple different ways that we can kind of look at it and try to determine this. But the rate determining step, and the rate determining step is sometimes abbreviated as the RDS for rate determining step. It needs to have pretty much the exact same rate law as the rate law that was found experimentally. So again, in a lot of mechanism problems, they will say the rate law was found experimentally to be this. When you kind of go through your mechanism, you will be able to sort of mathematically determine what the rate law should be based off of the mechanism. And what you should find is the rate law for the slow step, which is the rate determining step, should match exactly the rate law that was found experimentally in order for this mechanism really to be considered a good mechanism. So what is the rate determining step? It is, as the turtle shows there, it is the slowest step in the product formation. It is like the guy that has 500 items in the 10 items or less line. You are definitely not getting through that line until he is done. And that obviously is your rate determining step. it is really the one that determines, how fast a reaction will take place. It's kind of like this is the big hill that everybody's got to climb to sort of get to the other side. Perhaps the rest of them will go relatively quickly to sort of get to the other side. So let's just say, for example, you had, a two-step sort of mechanism, if you will, where maybe the first step was the fast step and the second step was kind of like the slow step in the mechanism. You know, how could you kind of see what's happening in that case? So for example, let's just say, let me see here. Let's just say, oops. Let me just do my made up example there. I guess we'll do that one. So let's just say we were looking at that sort of mechanism I was sort of made up the second ago, like, hey, A plus B goes to C plus D, and C plus D goes to E plus F, right? And let's just say that this was our rate determining step, our slow step here, the first step. And if we were sort of to diagram, sort of an energy diagram of what's happening, perhaps the first thing that we would see is something like this. And if we look at this, this would be like A plus B, right, or reactants, right? And the first hill it has to climb is this first step in order to form our C plus D, which is our sort of intermediates here, right? So the first step is really this one here, right? Bigger energy barrier. Once that step's over, the next step could kind of happen here where it will then go to our products, which would be E plus F. So this is sort of what you could look at in sort of a mechanism energy diagram. You typically will see, for example, in my example here, my step one, much bigger energy barrier, right, than when those intermediates then need to go through our products. And again, because this first step has the greater energy barrier, it's going to be really the one that determines how fast it can kind of get to the other side and make those products. So the rate determining step is really the important step there in the mechanism. It is the one that truly does determine sort of the rate of that overall sort of reaction happening. Now, how do we know, which one is sort of the rate determining step or which one is the fast step, which was the slow step? There's really kind of two different ways you could determine that. First off, if you are given the experimentally determined rate law, it should match one of the steps. Because remember that in a good mechanism, the rate determining step will have the same rate law as the one found experimentally. So one way you could determine, which one is sort of the slow step or the rate determining step is if they give you the rate law, it should actually match one of the individual steps. Like if you wrote the rate law for this step or this step, it should match one of them exactly. And again, you could do that because for each elementary step in a mechanism, you could write a rate law using the coefficients as those orders. The other way to determine sort of which one is the slow or fast step is a lot harder. It actually is a mechanism like this where they write slow and they write fast next to each of the steps. So the one that's marked slow in a mechanism sort of step would obviously be your rate determining step and your actual slow step in the mechanism. And the one that would obviously determine how much product you would sort of make or the rate at which the product would be made, I guess is a better way of referring to that. So again, in this sort of mechanisms type step, you could actually write energy diagrams. And what you should see is wherever the sort of slow step is, it should end up with sort of the, again, bigger hill to climb for those guys as they're moving from one step to the next. Any questions on that there? Okay, so let's talk a little bit about some different types of mechanism problems. We're going to see a few different sort of types, if you will. But there's a couple of ways that we study sort of mechanisms and reaction mechanisms. We measure the rate of a reaction. We try to formulate a rate law. And then we sort of try to come up with a plausible sort of explanation as to how this reaction could take place. Again, remembering that that's sort of what we're looking at when we look at mechanisms. As I mentioned earlier, it doesn't necessarily mean that, 100% of the time this reaction will always occur this way. Again, it could just be a plausible way of explaining how it could happen. You could maybe even come up with a secondary mechanism that also could plausibly explain how a reaction may actually occur. So let's take a look at one here. And why don't you try a couple things here first? Why don't you, what is the overall equation for this mechanism? What is the intermediate? And what can you say about the relative rates of step 1 and 2, given this information that the reaction between NO2 and CO produces NO and CO2? The rate law was found experimentally to be K times NO2 squared. It's believed to occur through these two steps. So why don't you take a few minutes and see what you come up with, and we'll talk about hopefully what you came up with and what you can get from this type of information. Be pretty straightforward. We want the overall equation or reaction is taking place. So that is found, I'll take my mess up here, by basically adding both of these together. Just like everything else we sort of talked about in terms of adding reactions, obviously anything that is on opposite sides of the arrow could either completely cancel out or sort of reduce down. So in this case, I see an NO3 here, I see an NO3 here. I also see an NO2 here and an NO2 there. And that looks like it for canceling out. That's going to leave us, again, everybody on the left-hand side of the arrow stays there. So that's NO2 plus CO. To everybody on the right-hand side of the arrow, which is NO plus CO2. And again, this would represent our overall sort of reaction here that's going to occur. Any questions on that there? That then leaves us to the question of what is the intermediate, and the intermediate here is NO3. Now you may be saying to yourself, what about NO2? I clearly canceled it out. And that is correct. You did cancel it out, but you did not completely cancel it out. And we see NO2 in the overall reaction. And remember that the definition of what an intermediate is something that's created early on in the mechanism, but gets completely used up by the time the reaction is done and really should not appear in the overall reaction. So here, because NO2 does appear in the overall reaction, some of it gets used up in this mechanism, but not all of it. So NO2 here would not be considered an intermediate. Any questions on that there? Okay. Now let's talk about the last one, which is what can we say about the relative rates of steps 1 and step 2? They clearly did not give us any information next to it like this is slow, this is fast, or anything like that. So remember that in these sort of mechanism problems, for each of these elementary steps that we have here, we could actually write a rate law. And if I wrote a rate law for step 1, it would be done like normal. It would involve just the reactants. So this would be the rate is equal to K times the NO2 concentration times the NO2 concentration, which would be NO2 squared. Might be an easier way to write that, I suppose. There we go. NO2 squared. Again, I kind of scribbled it up, but basically you got 2 NO2s on the side, right? And again here, this one limited time when you can do this, coefficient will become the exponent here. If we write a rate law for step number 2, we see that the rate is equal to K again times our reactants, NO3, and our CO. So from this mechanism, from each of these elementary steps, these are the 2 rate laws that you can do for each of those steps. Any questions on that? What do we know about sort of the rate law for the elementary step and the rate law that's found experimentally? We know that if it is a good mechanism, the rate law that's experimentally found should equal the rate law for the slow step, or the RDS. Which means if we look up here and we see the rate law that was found experimentally is the rate is equal to K times NO2 squared, that matches perfectly the rate law for our first step. So because it matches perfectly the rate law for our first step, we can very confidently say that step number 1 here is our slow step, also known as our RDS. We could imply that this step, step number 2, would be a faster step than that. So what we know is that step 1 will occur slower than step 2. And it's basically step 1, which is our rate determining step here, that will determine how fast this reaction will really take place overall. Any questions on that? So this is one type of mechanism problem where they really don't kind of individually tell you which step is the rate determining step or the slow step. What they basically will tell you is the experimental one, and what you would expect to sort of find here is using that information and the rate loss for each step to determine which one would be the slow step. So, if we sort of drew this energy diagram, just roughly sketch it, we would have our 2 NO2s, which would be our reactants. Step 1 would be, again, that big step coming down to sort of our intermediates being formed, badly drawn here, NO plus some NO3, not both intermediates, obviously. And the next step should occur at a much sort of smaller hill pace, where we get to sort of our full products being formed, really are kind of NO2 plus our CO2. And again, these obviously, this guy being canceled out here, but this would basically be the hill, if you will, for step 1. As you can see, a much smaller hill for kind of step 2 in this mechanisms. And again, the overall energy difference, and again, I don't know if it's exothermic or endothermic here, but this would be the delta H of the reaction, the difference between those two. But again, this is sort of how, if you were drawing sort of an energy diagram curve, you would expect to see, again, a larger hill for that first step, much smaller hill for that second step of the mechanism, into our sort of products being formed. Any questions on that there? All right, so yeah, let's take a look at another type of mechanism problems, and we'll go through this one together to kind of show you sort of how you deal with a mechanism problem such as this one. And this one looks a little bit different, obviously, than what you've seen here before. And if we look at I'll just put it here. So let's say in this reaction, the overall reaction is what is observed right here, I think, right here. So for this particular reaction, this is the overall reaction is taking place. This is basically our experimentally found rate law. And this type of mechanism problem is a little bit different than the one we just did. I sort of equate this to a mechanism problem like a proof, if you will, like you kind of know the answer, but you need to prove that the answer is correct. So this is sort of this type of mechanism problem. You want to kind of use the mechanism to determine, you know, is this a good mechanism? And again, here, what we're looking for really is two things. We need to add up all the individual steps and determine, does it equal the overall reaction? And if that's true, then we need to determine, does the rate law for the slow step equal the rate law for the overall step, or the experimental rate law? So let's see how we could do this. Let's start with the first thing, which is sort of the easiest thing. We want to really add up all the steps here and see, does it equal the overall reaction? So I'm going to do that right here by just putting a big plus sign there. And we want to probably do a little bit of canceling out. So let's see what we could maybe cancel out here. Just looking at it, looks like the N2O2 will cancel. It looks like perhaps the N2O2 here will cancel, and N2O will cancel. And it looks like perhaps that is it in terms of the cancellation. Now, keeping everything on the left-hand side of the arrow, I end up with 2NO plus there's an H2 and an H2, so that is 2H2. And that is going to our product side, which is the right-hand side. I have 2 waters, and I have an N2. A lot of reactions to see that match, 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 and match. So the first part's good. We have basically, when we add up all of these elementary steps, in this case there's 3 of them, and we add them together, we do end up with the same overall reaction of what we're looking for. Any questions on that so far? So now what we need to determine is, will the rate law for the rate determining step match the one that was found experimentally? By the way, we could also look at this and determine that in this particular reaction, there actually is 2 intermediates, right? The N2O2 is an intermediate, not found in the overall reaction. The N2O is also an intermediate. So there's actually 2 intermediates here in this particular reaction. All right, so what I'm going to do now is erase some of my cross out marks here so I can actually see what's going on. Everybody see what's going on. There we go. So first off, we want to determine which one is the rate determining step. So that's fairly easy. They were nice enough to label this step as fast, this step as slow, and this third step as fast. Because this one was labeled slow, we automatically know that is our rate determining step. That is the slow step in this mechanism. Any questions on that? All right, well, since the slow step in the mechanism needs to have a rate law that matches this one, we might as well start by writing the rate law for the slow step. So if we write the rate law for the slow step, which is step 2, the rate law for step 2 would be the rate equals K times H2 times N2O2. First off, any questions how I got that? It just strictly focusing in on the second step here. Now, what I need to do is go, does this rate law here match this rate law here? And you may say to yourself, no, it does not match. And you may be right, or you may be wrong. The reason you may be right or you may be wrong, which I think is a song title, I'm not sure, but this is N2O2 here. N2O2 is actually an intermediate. And the problem with sort of comparing a rate law that has an intermediate in it to obviously the rate law for the overall reaction is we're not really comparing apples to apples. So we do have to do some math here to basically get the rate law for our slow step into a rate law that does not contain usually the intermediate. So that's going to require us to do a little bit of math and a little bit of substitution so that we could get a rate law for the second step that is sort of apples to apples and we can compare them. So what is really the goal of trying to convert our rate law here into a more usable one? We kind of want to get rid of this guy. We want to get rid of that. And we want to basically substitute it out for something else. Where can we go to do that? We could actually use other steps in the mechanism to help us do that. For example, the only other step in this mechanism that has N2O2 in it is step number 1. Now, you may also notice step number 1 is a little bit different than the other steps because it actually has a reversible reaction. Right? And we talked much this semester about reversible reactions. That means that there is a forward direction, right? And there is a reverse direction. And at some point, the rate of the forward direction will equal the rate of the reverse direction. That is the whole basis of equilibrium, pretty much the entire class that we talked about this semester. So how can we use this to our advantage? Well, we can actually write for step number 1 in this case, because there is basically a reversible reaction here, we could actually write 2 rate laws. We could write a rate law for the forward step, and that would equal K, and the forward step meaning it going from reactants to products, K times NO squared. We could also write a rate law for the reverse reaction. In the reverse reaction, we would be heading in this direction, right? For step number 1, which means our products become our reactants and our reactants become our products. And if we write the rate law for the reverse direction, it would be K times N2O2. First off, any questions on that move right there? So those are the 2 rate laws that we could get for this reversible elementary step that's occurring in this reaction. How is that going to help us? Well, we just talked about a moment ago that the rate of the forward direction will equal the rate of the reverse direction, which means although we don't know what this number is, that number there and that number there should actually equal the exact same number, which means if they equal the exact same number, you could actually place them equal to each other. So if I take my forward rate law and set it equal to my reverse rate law, you could hopefully start to see that perhaps I'm getting close to what I need, right? Because I need to get N2O2 here basically to substitute out. And I could do that, and if you want to be technical about it, this would be, right, the forward direction, that would be the reverse direction, or it actually would be 1 and minus 1 in this case. We're going to divide the K value to the other side. That will give us, I'll use the right K's then, K1 times NO squared divided by K to the minus 1 equals our N2O2. I'm really just dividing this K value to the other side, basically. Any questions on that there? Now I have an expression that I could take and substitute into my original guy. I could take this entire thing because it equals N2O2 and basically put it right into there. Any questions on that so far? All right, now putting that in there, we can now perhaps get to something that we could use. So here we go, just putting everything in. The rate equals K times H2. I'm now going to substitute in my guy from the bottom, so I'll write it just like that, K1 NO squared divided by k to the minus 1. Okay, 1 there. Any questions on that? Now we have a lot of k's going on there, right? And what are all these k's? These are all rate constants, which means they are technically a constant number, which means this k and this k are essentially the same. And that means that those two will really cancel out. And now that we clean it up, we end up with a rate law for our second step, or rate determining step, of k is times H2 times NO squared. Now we can compare these two, and do both of these rate laws match now? And when we look at it, we can actually see that yes, they do match now. That means that we have met really the two requirements for this mechanism to be a good mechanism. First off, all the steps add up to the overall reaction, which was the very first thing that we did. And now that we were able to substitute out sort of that intermediate and get a rate law that has pretty much everybody that's there in the overall reaction, we could clearly compare apples to apples now, and we see that both the rate law that was found experimentally matches the rate law for the slow step, which means that this is technically a good mechanism or a plausible mechanism to occur. Any questions on any of those steps there? Let's see here. All right, so why don't you try one now that I've done one? So for this reaction here, 203 goes to 2302. I'll write it over here maybe because it kind of got spread out over there. There's the reaction. Is this rate law or this mechanism a good mechanism? This is the experimentally found rate law. So take a couple minutes, not only say yes or no, but you need to prove it, right? Also, while you're there, why don't you determine the intermediates? All right, so take a few minutes, prove that this is either a good mechanism or a bad mechanism based on the information given to you. Okay, so let's take a look here and see. So remember, in order for us to determine if this again is sort of a good or bad mechanism or a plausible mechanism, what we're looking for really are those two things. We want to make sure that when we add up all the steps there, that it should equal, in this case, the overall reaction that we're looking for. So that's usually a fairly good place to start. So we could just simply do that by obviously adding these together. Here looks like we see an O and an O cancel, and at that point that looks like it. So we end up with 203 goes to 302, so that's looking good. So that matches here our overall reaction. So that is good. So the next thing that we need to basically determine is, does the experimental rate law that was given to us here in the problem, does that match the rate law for basically the slow step or the rate determining step? In this case, they obviously gave us the fast and slow indications next to it. So without much thought, we should know that this should be our rate determining step, as it's marked the slow step in the mechanism. It also should tell us that the rate law that we determine for our second step, which is our slow step, should match this rate law, again, if it is a good mechanism. So we can, because this is a mechanism in an elementary step, for step number 2 there, we can write our rate law, and that would be the rate is equal to K times our O3 and our O. Again, we want to compare the experimental one to the one found here at our slow step. And again, if you want to think of it this way, we got that intermediate there, and we cannot really compare apples to apples here. You may look at that and go, I don't think it matches. Obviously, that has an O, the other one doesn't have an O, but because that intermediate is there, we do need to, again, do a more kind of substituting out and get rid of this intermediate. So we kind of want to get rid of that intermediate. So in this case, there's really only one step to turn to, since there's only one more step in the mechanism. And again, much like the one we just did, we do see a reversible reaction happening here. That means, again, we can write two rate laws for that first step. We could write the one for the forward direction, which would be the rate is equal to K1 times O3, again, assuming we're heading obviously in that direction. We could also write a rate law for the reverse reaction, assuming we are heading in this direction. And that would be the reverse reaction here, which would be the rate is equal to K to the minus 1. Now our products become our reactants. So that is the concentration of O2 times O. Just like we talked about previously, because it's a reversible reaction, because it will reach chemical equilibrium, this rate and this rate will essentially equal each other. So that's what we're going to use to allow us to basically set each of those rate laws equal to each other. Any questions up to that point? Again, the purpose of doing this is to remind everybody we are looking for this guy, O, and we see him right here. So rearranging what we just did here and solving for O, O would equal K1 O3 divided by K to the minus 1 O2. And that is the guy that we can now use to substitute in to our original rate law we had for our slow step and basically put it right into that spot. So let us do that, and let us do some cleaning up of it as well. So if we just go straight in on that, that is the rate is equal to K times O3, the fancy bracket, and substituting in our bottom guy there, our K1 O3 divided by our K to the minus 1 and our O2 in this case. Any questions on that so far? Now you may look at that and go, okay, I'm ready to compare this and this. And you may say to yourself, maybe it doesn't look the same because there's a lot going on there. So you might want to, again, take a moment here and kind of clean up it one more time, remembering that we now have 3 of our K values there. They're all rate constants. So again, basically these two cancel out. That leaves us K times O3 times O3, which is O3 squared divided by O2. Now you have something that you could compare this guy to this guy to. And when you do, you should see that, yes, they do match. You may say it doesn't look like they match, so you could clean it up one more time if you want. The rate here would equal K times O3 squared O2 to the minus 1. O2 to the minus 1 is basically 1 over O2, which is how it gets to the bottom over here, right? So it's the same thing. So in this case, they actually do match. And this means, again, here, this would be a plausible mechanism for how this reaction could take place. Again, the two main things, everybody adds up to the overall reaction. The rate law for the slow step matches identically the rate law that was found experimentally. Any questions on any of those steps there? Now, what happens if one of those two things don't match. So again, we talked about if you add up all the steps and they do not match to the overall reaction, then it's a bad mechanism. If you add up all the steps and they do match, then it's good. But then if you get to the part where you're comparing rate laws and they do not match, then it would be a bad mechanism. So again, both of those things has to happen for it to be a good mechanism, or plausible mechanism is sometimes referred to. Again, if something does not match, then it would be a bad mechanism. It really wouldn't occur via that proposed sort of steps. Any questions on this type of mechanism problem? All right, so let's take a look at one more mechanism problem here, I think. Why don't you take a moment here? You want to determine the overall reaction here. You want to determine what is the rate determining step. You want to write the correct rate law for this reaction, and you want to identify all the intermediates that are present in this mechanism. Go. Okay, so in this case, a little bit different than the couple other mechanism type problems we looked at already. Remember the first one, they sort of gave us the rate law and wanted to know sort of, what's the difference between sort of the different steps. The other one we just looked at, a couple there, we are given the rate law and sort of a mechanism how to kind of prove that it's good or bad. Here, we just want to try to determine sort of everything that's going on. So first off, we'll start with the overall reaction here. Simply, again, like we've done before, we're going to do some adding there. It looks like it is B that gets canceled there. That's going to leave us on the left-hand side 2A plus B little 2. We'll go to the right-hand side 2AB in this case. So this is our overall reaction. We want to determine the rate determining step. That is easily determined for us because they did label this one slow. So that would definitely be our rate determining step. What do we know about the rate determining step? We know that it should have the same rate law as the one that was found experimentally. So we can simply write our rate law like we would for this elementary step by taking the rate is equal to K times A times B to the 2. And this should be both the rate law for the RDS and thus the rate law for the overall reaction. We also see that we don't have any intermediates in there, which is good, right? Speaking of intermediates, we see in this case that B would be our intermediate here. So again, we can very easily sort of justify what we've been talking about, that, if we were sort of following the energy diagram here, we again would expect that first step to come out pretty big. Second step, not so much in this case. Again, step 1 here versus step 2. And again, here we would have our A plus our B2. Down here, this would be the formation of these guys. And finally, our formation really of our product over here. And again, this sort of hill that first step has to climb much bigger than the hill that the second step would have to climb in that particular case. Any questions on mechanisms, how to work mechanism problems? And these are the common things that you're sort of asked is, being able to identify intermediates, what the overall reaction is, being able to write the rate law for the based off of the mechanism and comparing, does it match? And is it a possibly good mechanism or bad mechanism? Again, here, the couple or few examples that we did, they were kind of good mechanisms, but they may not always be a good mechanism. And again, if one of those two things don't match, either the overall reaction or the rate law for the slow step, then it's going to be a bad mechanism. Any questions on any of that there? Okay, so finally here, we're going to look at catalyst. So we talked about catalyst a little bit earlier on as well, and the catalyst, for the most part, when somebody mentions a catalyst, they usually are probably speaking about it in terms of sort of speeding up the chemical reaction. But there are things that are, again, referred to as sort of negative catalysts that will kind of slow down a chemical reaction. sort of a similar analogy is like, again, like what we talked about in nuclear chemistry and sort of that nuclear power plant where they, insert some like cadmium sort of control rods and stuff like that. And it basically grabs out, for example, the neutrons in that reaction. And again, the idea of that is to slow down a particular reaction, but probably again, 9 times out of 10, most people are thinking about it in terms of it speeding up a chemical reaction. So a catalyst also you should remember is, again, not considered a reactant or a product. So it's not considered really a reactant or a product. It does not get used up in the reaction. It is there really just to sort of facilitate that reaction happening faster in most cases. Where do we usually see catalysts a lot of times written? A lot of times on top of the arrow, maybe something like platinum, some type of metals listed there. You might even see like H plus to indicate that it's like an acidic conditions is the catalyst, maybe like basic conditions sort of situation, or a base listed up there like sodium hydroxide or something like that. So a lot of times in reactions on top of the arrow is sort of where we do put that catalyst listed. So how does a catalyst sort of speed up a chemical reaction, for example? Well, catalyst basically, if you want to think about it this way, sort of finds a alternative pathway, if you will, to allow the reactants really to sort of come together a lot more efficiently, I guess is a good way to put it. Rather than if the catalyst wasn't there, they're just kind of maybe floating around, flying around, and hoping to come in contact with each other. Sometimes a catalyst can work by actually being a place, like a gathering place, if you will, kind of attracts everybody to a centralized location. And obviously, if everybody ends up sort of near each other, that's going to facilitate really the reaction occurring a lot faster. So that's, sometimes how solid catalyst works. They sort of, kind of bring everybody in, sort of help along with the breaking of bonds and sort of the reforming of new bonds as it's sort of occurring near or on the catalyst. And then they're kind of free to kind of go off after that point, rather than, again, trying to find each other just without it present. Ultimately, when we sort of think about how a catalyst works, we sort of think about these energy diagrams. And ultimately, what a catalyst it does is it lowers that activation energy, kind of finds, again, that more efficient, if you will, alternative path for a reaction to take place. The result of that is we would expect to see the rate constant or the rate increase as a result of that. So instead of A and B over here having to climb this big hill, with the addition of a catalyst, it now has a much smaller hill to climb, which obviously means it could probably get over to the other side a lot faster. It's kind of like the old Roadrunner cartoons and stuff like that, right? Instead of having to go up and over the hill, right? Finds like the trap door and just goes straight through to the other side. So obviously, if you were walking up and over the hill, it'd take you much longer if there's like the trapped cartoon door that you just go right through, the middle of the hill to get to the other side. And again, that's sort of how a catalyst works. So what we typically see is the rate of the catalyzed reaction is usually a lot faster than the uncatalyzed reaction. Again, proximity wise, everybody's kind of near each other. And also, again, that's going to allow everybody to start reacting a lot faster than, if they had to fly around. A reminder that, as we talked a little bit about in that previous chapter, that, just because we have, for example, a spontaneous reaction, it doesn't necessarily mean that the reaction occurs super fast, right? It could be a really, really slow reaction, but it would occur spontaneously if you left it there. Something like ammonia, we'll see here in just a second, occurs super, super slow. But if you add some catalyst to it, it could definitely speed up that rate of the reaction. So again, it occurs slow because, it's going to take a while for everybody to kind of come in contact with each other. Adding that catalyst sort of rushens that or moves that sort of process along a little bit quicker and a little bit more efficient. ultimately meaning that they don't have to go so long to get up and over. You also probably have a little bit more people that can sort of get to the other side a lot quicker. Now, when we talk about catalysts, there are different types of catalysts. There are ones that are sometimes referred to as a heterogeneous catalyst. So kind of like a heterogeneous mixture. It means, again, heterogeneous means you see sort of different layers or different phases, right, when you have a heterogeneous mixture. And that's sort of the same idea here. A heterogeneous catalyst is basically one where the catalyst and the reactants are basically in different phases. So for example, ammonia is basically N2 and H2 coming together. Those are gases. And we could use some type of solid catalyst as a way to allow those guys to come together a lot quicker. Again, it's a spontaneous reaction, but a very slow reaction if you don't include sort of the catalyst. Also, for example, the production of nitric acid is also a very catalyzed reaction. Our catalytic converters in our cars, right? If you have a catalytic converter there, you got basically two chambers, got a couple of different catalysts in there to sort of help in burning off or converting some unburned hydrocarbons and kind of cut down on pollution along the way as well. Oftentimes in labs as well, you know, we oftentimes, especially when dealing with solutions, we'll deal with homogeneous type catalysts. And these are really where the reactants and the catalysts are basically in the same phase. So common ones are acid catalyst and base catalyst. And again, here, you know, by adding some acid, as we talked about throughout the semester as well, right? It's just, you know, playing with the pH and so forth, creates the right environment and allows things to be perhaps more reactive. You may be sort of protonating something, deprotonating something, allowing these things to kind of come together a lot quicker. And again, that obviously would be if you're dealing with a solution and you're adding an acid or a base, probably everybody is an aqueous sort of environment and they're all the same. So here's that Haber process. And again, the NH3 got hidden here. It's actually not a catalyst here. Sorry about that. There we go. So we have our N2 plus our 3H2. And again, you can see a bunch of different metals can act as a catalyst here. And that's sort of what we see here. This would be a heterogeneous catalyst. This is the catalyst. These are our gases, or hydrogen gas or nitrogen gas that are flying around. And you can see it's kind of like a landing pad, if you will. It's, you know, these guys are going to be kind of drawn to this. And as they're drawn to it, it's going to help with some of the redox or stuff that might be happening, some breaking of bonds and those type of things, going to allow these bonds to sort of break a little bit, also allow these guys to start to come together, you know, to kind of make our ammonia that's happening. And it's sort of like a little area where they can kind of all come together efficiently and form, you know, our products there on the back end, and they can release. You can see that the catalyst here is really unchanged in this reaction. Again, it's really there for that purpose, to facilitate this reaction happening a lot more efficient than it would normally. And again, it would be more like this bonding, I suppose, is a better way of drawing it. Nitric acid as well. Oh, my arrows got all messed up. But you get an idea where the arrow would be here. There we go. So platinum catalyst being here, this is actually sort of a three-step process sort of happening in this sort of reaction. We got some ammonia making some NO and some H2O. That NO and some O2 make NO2, then combines with water to actually make two acids. It makes the nitric acid, which is kind of what it's trying to make. And it actually makes HNO2 here, which is the nitrous acid. And the interesting about this thing is the nitrous acid actually basically doesn't hang around a long time. It actually decomposes into some NO and some NO2. So in the process of actually making the nitric acid, you're making this nitrous acid, which will eventually decompose pretty quickly and actually refeed sort of the whole process. So it becomes a relatively sort of efficient sort of process that's occurring as sort of your product is actually feeding your your reaction, and it kind of keeps it going and stuff like that. So that's sort of an interesting thing there in that sort of formation. As we talked about here with your car, you have a catalytic converter, usually has a couple of compartments. You look in there and maybe it's got like a little honeycomb type situation that has a bunch of, metals in there that help to cut down on some unburned hydrocarbons, which are carbons and hydrogens, and make basically CO2 and water. Also cut down on some of the nitrogens byproduct that happens as well, and make some nitrogen gas and oxygen gas again as it kind of goes. Obviously, your combustion happening here in the engine, all those sort of uncombust gases and other gases go through obviously your manifold into your tailpipe, and also goes through these two sort of processes. The idea there is clean air coming, hopefully, or clean stuff coming out of the tailpipe if everything's sort of operating correctly, or a lot more clean stuff coming out than obviously if it wasn't operating very correctly. Any questions on catalyst? All right, well, that officially ends the lecture material. So congratulations, that is the end of one